Donc, bonjour à tout le monde. Hello, everybody. So today we want to present you some possibilities and some examples for the implementation of future-oriented technologies in the sector of nuclear waste treatment and in the use of deep repositories. So we are Thomas Ertl as a sales manager within Bilfinger in the business line nuclear, and my colleague Petra, who is leading the engineering department for specialized equipments in this area. And we are happy to present you a little bit of our projects we do at the moment.
So, thank you. So, first to start, we would like to give you an overview over what we want to talk about to you. Because future-oriented technologies could be everything. And what we want to show you today is a little bit about building information modeling, process simulations, digital twins, virtual reality, different analysis and calculations, and remote handling, and last but not least, a little bit about automation. So, Tom, it's up to you.
So, and therefore we will dive into two different projects, which the first one is already completed and the second one is currently ongoing. And the first one we were talking about is the ISEDA project, which was built for EDF. So what is ISEDA? It is owned and operated by EDF and based in Bugey on the location of the nuclear power plant. It's a facility for the conditioning and the treatment of different nuclear wastes for preparing them for the intermediate storage. And the installation, as you can see here above, is divided into three sectors, which is a reception and a waste transport hall, which is the process block with three hot cells for the conditioning of the radioactive waste. And there is also a storage hall for the waste packages after treatment. So in our scope, there were the process block, including all the hot cells. So what you can see here on the left is the first hot cell we delivered, which is a quite complex one. The waste is brought to the hot cell underneath the ground, is then unloaded via this with special equipment here. The waste, which is packed in special transport cases, so-called etuis, is then unloaded with specialized grippers, is put into a buffer storage underneath the ground as well. And when it is needed for treatment, it will be brought up again and will be brought to the first cutting table, which is the cutting table for the control rods. And therefore, and this is what you can see on these pictures here, the etuis are gripped and then placed on the cutting table, are tilted afterwards, and then the control rods fall out, and then they are treated and cutted, which we see afterwards. The cutting process in a little bit more detail. For the control rod, it is done via hydraulic shears, which you can see here. They are gripped and moved forward, and then between the two cutting rods here, they are hydraulically cutted and then placed into the metallic drums, which are used then for concreting afterwards. Also, the transport cases have to be treated and cutted. So once they are empty, they are placed on the second cutting table, and then they are cutted with a bandsaw, as you can see here. And afterwards, they are also pressed with a high pressure hydraulic system. And this is what you can see here. And once the etuis are pressed, they fall also into the metallic drums in order to reduce the volume of the waste afterwards. And afterwards, when everything is done, the filled metallic drums are transported to the next hot cell in order to start the concreting process. This is the next hot cell we delivered the equipment for, which is the first grouting cell for the metal drums. So when the metal drums are filled with the waste, which was cutted before, there is concrete coming through wall penetrations into these drums to fully concrete everything, every small room, so there is no empty space anymore for between the wastes and the drums. There are also, where this you can't see it here, but if necessary, there are also vibrating tables where the metallic drums are based on, in order to ensure that there is an even distribution of all the concrete and there are no gaps anymore, no air bubbles in between and so on. And after everything has dried, these metallic drums are then transported into a so-called washing machine. So it is another washing machine, so not as you have at home, but specially for the metallic drums. They are inserted in there. Afterwards, they are washed in order to get rid of all the loose contamination. So this could be contamination resulting from the cutting processes and so on. So just the little particles, they have to be removed. They are washed out, and afterwards the metallic drum and the concrete surface is dried and moved on to the next hot cell, which is this one. Then the metallic drum is placed into another drum, which is made of concrete and stone, the so-called C1 PG drum. And this is like an over-packaging. And as you can see on the right side of the picture, there is still a gap between these two different drums. And the first process step there for concreting is to fill this gap. So there is another type of concrete inserted into this gap. Afterwards, you can see on the right side that this gap is no longer there. And after this step was finalized and it is dried, the next and last step for processing is made, and this is the cover concreting to ensure an even surface on the final drum. As you already can see here, all this is remote handled, and we will just talk about it in a second. But you can see here it is like you do it by your own hand, but with a parallel manipulator and behind a shielded window, in order to protect all the operators. Then the last step of the process is the lifting and the transport of this C1 PG drum towards the last small hot cell, which is only there for the radiological testing for the end, including smear testing, and afterwards the finalized drum is transported to the intermediate storage facility. So what you can see here is then the outside of the hot cell, so in the operating rooms. The technical challenge we had while realizing this installation is that there is basically no human intervention possible in this hot cells because of radiation. And so therefore everything has to be fully remote controlled and also to be operated from external, so from the couloirs. Also, in case of maintenance and repairs, all the equipment have to be demountable fully via remote controlled devices and remote handling devices, in order to bring them to different cells, which you can see here. This is a maintenance cell, and this is also a maintenance cell, and this here is the hot cells we saw. And every equipment can be brought up there, and there a human intervention for doing maintenance and so on is possible. So we have brought two examples how this looks like. The first one, the vibrating tray, is part of the first cutting table where the control rods are in. So also this equipment is fully demountable via remote handling devices, so you can unscrew and rescrew afterwards, which was a technical challenge to get there. And the second one is the full removal of the washing machine, as you can see there. And on the right top side of this picture, you can see that there is the maintenance cell where it is brought into. And again, a few pictures how it looks like in the control rooms. So you have the radio protection windows, where you can have a direct look into the hot cells. We also have video systems in the cells, which helps for orientation and so on. And as you can see here, all the operations are done from displays, including crane handling, including heavyweight manipulator handling, and also the handling of the parallel manipulators. Now, coming back to the future-oriented technologies, also this scope was designed in a 3D model, which was existing and a little bit enriched with further informations. We modeled the whole process into the 3D model, so you can see it in virtual reality afterwards, after rendering. And here there are just some examples of how documentation is provided for the different steps of the process. And afterwards the results of the simulation can be seen also at our booth. We will mention it once again then. And it is a really nice tool for presenting results to the customers for early detection of potential problems before even delivering some equipments to site, like doing interface checks or do not oversee interfering edges, all these kind of things which are quite normal in a construction phase. And it is a nice possibility also to see the building and the environment of the installation done already before realizing it. So, and this is then the comparison. So it is the 3D model. Afterwards, it is the real photos we took. So it is quite similar and quite near to the reality what we have in the 3D model.
Okay, now I would like to present you another project we are doing at the moment. And this is for remote handling in deep repositories as an example. But what we do at the moment is something different of this. We are developing a complete remote controlled retrieval device for recovery of drums in a mine in Germany. So our challenges here is that nobody can enter it, that we don't know the situation, what we will find there, and that the waste we have to put out of this mine is part of it is covered with salt, so we cannot even see it at the moment. What we do for this project is that we have chosen an excavator, and we use this excavator as a tool carrier system on which we make the whole engineering for remote handling and automated control. This means, so we make mechanical adaptations on the system, we make the control engineering, we implement detection systems on it. We make all what we do with this system with process simulation, and we have built up a digital twin, I will show you afterwards. And at the moment we work on automated processes, because this is very important for the operator, because this handling of these complex machines, I will show you, is very tiring. And so we are working on this. What we do on our side is we build realistic test setups, and we test all possible situations with our components and our systems to optimize it and to develop the whole process and the remote handling for this. So here's a short overview of our excavator. What you see here, it's a 20-ton machine, which we have special upgraded. So we have a radio control system already on this machine. We have a tool management system. This we need because we have to use different grippers, different tools, and we have to change this all the time. We have a tilt rotator on it to have more kinetic degrees of freedom for our works. We have a fully automated coupler on it, different camera systems, and already also sensors for the digital twin we need. And the machine also has a load retention and stroke and swivel limitations. So what you see here now is one of our test areas, where we have a chaotically stacked of 200-liter drums, where we try here with radio remote control and with direct view of our operator. So he is standing beside it and he is moving around. You can see here. And this is the normal process with radio remote control, and you see the difficulties we have. So at this moment we have not optimized the movements of this machine. You see 4 different views from 4 different cameras, and so the process here is accelerated. What I showed you the video, normally it took something between 5 and 10 minutes for an experienced operator to do this, what I have showed you here. And this is under direct view. If you want to make this remote controlled with camera systems, it's even more difficult to do all these actions. What we have done then is we adapted this machine for remote control. We have mounted some various camera systems on it, so on lots of different positions to get the field of view for the operator. We have implemented sensors for the angle measurement. We have 3 LiDAR sensors on it to record the position and the attitude and the speed of the movement and of the joints. And we have modeled all the kinetic components to realize a digital twin of this tool carrier system. And this is the first step for us to come to an inverse kinematics like robotics have it. Because we have seen how complicated it is to work with this machine without having an inverse kinematics. So if you have the inverse kinematics, you can point to the point where you want to go, and the machine is looking how it's done. It's doing it. So all the joints, everything is moving automatically. And here you can see now our digital twin. This here is the image. It's a live image of our LiDAR sensors with the machine, and on the top of the video, you see a camera. A video from a camera we have taken. And you see here we tested all different movements with the machine, and you can see it really without time shift in this LiDAR system. So the LiDAR systems also help us to localize all our joints, our positions, and for obstacle detection. Because in the situations we need this machine later, we will have a lot of obstacles. And we have to avoid crashes or something of this. So this is finished. So on the next video now, you see the inverse kinematics we have already implemented. We have a path execution on the tool carrier joint system. And at the moment, our point is here. It's not already defined in the tool, it's on top of it. And you can see here the image our operator sees on his computer, and he's operating now the tool center point with a 6 degrees of freedom space mouse. So now it's not more the radio control, now it's controlled by a space mouse already, this movement. And the next step now is to come from this inverse kinematics to a complete remote control and operated system. So I think the video, yeah, it's done. Yeah, what we are working on at the moment is the problem with the view. So we have at the moment to operate the system between 7 cameras on the system to see our tool, and this is the point where we want to work. And we have 3 cameras around it. And even that makes it very difficult for the operator to have this 3D image our normal eye can do. And for this we are now working on the possibility to make semi-automated processes for repeating process steps, like tool change or things like this. And for this we work here on the design of operational control and to help and to assist the operator for his tasks. So this is what we do on this subject. All what we do here, we accompany with simulations. So what we have done for the design of the real machines, what I showed you before, is only a machine for us to implement these technologies. And what we do now, is we have to build up the machines like we need it for the task, for the real tasks there. And for this, we make process simulations to see is the size enough and everything, and to see critical points in all our processes. Then we support all our designs of the machines, of the components, with load bearing capacity, with the functionality, and to show the integrity under operating and also under fault conditions. Another point we do, depending on the task we have, we make static and stationary calculations on analysis to see already now during the development what we need and what we have to do. And then we also make dynamic analysis because in the nuclear, like most of you know, we have to show that everything is okay in earthquake actions, if you have accelerations caused by an airplane crash or something else. So this all we do for our components. And last but not least, we make simulations to see highly time-dependent or non-linear behavior of action and of effects we have on our structures. And now I would like to show you some examples of this. So here you see again, it's a tool carrier system. Now it's a little bit a different system like I showed you before. This is an example of a 60-ton machine, so it's much bigger. And what we have done here is we have all our degrees of freedom, all our possible motions. We have put in a simulation software, and we have done simulations with to see the operating distances of the system. It's possible to reach all the critical points. We have done. We have seen some collisions with other infrastructures we have in the situation. And another point is, like we are working in a mine, we have to know where we need light to see something. So we have also done illumination and camera simulations with this software. And now I show you shortly this. You can see here. This is as part of our simulation. So it's I think with an acceleration of 20. So it's very fast. And here you see the machine is coming. A tool is placed, we make a tool change. So we have already inverse kinematics on the machine to show it's taking the tool change, and this all we have in a VR video. So you can come to our booth and see this if you want to see it completely with a VR video. And it's not only this process you can see, the tool carrier, because I think we are a little bit off time. So the video takes 2 minutes, so I will stop with this now. But you can join us in our booth and you can see it there. We have it there, the whole process. Because this was only the tool change, now we make a cutting process. And afterwards we have several other processes simulated here. So what else I would like to show you is we did special simulations. Like you have seen our test before, we have a lot of drums and we have to recover these drums. And if we have some problems with our grippers or something, it could happen that a drum is falling from 1 meter to other drums. And this is a situation we have to avoid. And we tried to see the impact of a full drum with 1 ton on an empty drum from 1 meter. And you can see here now, this is a simulation we did. The drum is falling and it's decreasing the other one, and it's really going on it. Here you will see only the lower drum, and here you can see the impact of the other drum. And you can see how the energy dissipation is in this drum inside here on the other simulation. And on the right hand, you see the velocity. So we did these simulations, and then we have done an experiment to validate our simulations, to see if it's realistic what we have done. Now, yes, you see it. So this was the impact of our drum from 1 meter, 1 ton here, empty drum here, and you see it has still its integrity. So it's damaged a lot, but it's not collapsed completely. And here on the right hand you can see how it looks like. It looks very similar, or it's nearly identical with our simulations. So we did a lot of experiments to validate our simulations with this. Here you see another thing. This is a more body simulation where we try to show how is a falling drum moving and where could it be afterwards on the left-hand side. And here you can see another simulation. If you have an embankment and you have problems and the embankment will collapse. And here the task was to measure the angle of repose to see what is happening if you have a collapse in your embankment. This is on the right hand. So, and to finalize our talk today with lots of different subjects, we have another simulation here you see on the right hand. Also for building up our machines or for repair or for something, we need to know our welding processes. What you see here is an example of a first layer of a weld joint between the nozzle of a nuclear pressure vessel and the connecting pipe. So this was a work where we had to repair in a plant this situation. And before doing this, we have done this post-weld heat treatment simulations to see. And what we have seen here on the side is, let's show again, the weld head going around the welding joint, and you see the temperature response on it, and how this temperature is staying in the material. So this is also a very important thing if we do repairs or something on a plant. Yeah. So I think this was the last video. Here it's coming again. See it? So I would give to Tom for the outlook.
Yeah. So really short, what we wanted to present today is a bunch of different future-oriented technologies, how we called them, which we did in different projects. And there are, of course, other things like artificial intelligence which have to be integrated in the simulations and in everyday work, and also machine learning, automated learning, and so on. And there we are currently working on it, on implementing and doing these things also in the future projects. So we would be happy to host you at our booth, which is F092. Show you our virtual reality course. And yes, thank you very much for your attention. You're still our contacts. And thank you for your attention.